So our last chapter on vectors. So what makes something a vector is when it has a magnitude and a direction. Now, magnitude could be a weight, a speed, some sort of measurement. Okay? Something that just has a magnitude is called a scalar. So what makes something a vector is not only do you have a magnitude, 5 kilometers, in a certain direction. Is weight a direction? Because it has gravity? Or is you're saying because...
It has a vector can be weight. You said that, right? What's the direction?
No, you had said when you were explaining that weight was a vector.
I said weight?
You would put weight in the list for vectors.
I did?
I don't recall
When
that.
you said it aloud.
Oh, I don't think so.
I kept on saying the rock was 5 kilograms. That must be it.
No. Weight on itself. Oh, yeah, it is a magnitude, but not a, like, doesn't have a direction. Unless you...
I guess we misunderstood.
Yeah, because I'm really confused right now as well. Any kind of measurement. So, we have a list here. Your job is to figure out whether you think something is a scalar, a vector, or neither. And then we'll go through the list. You can put S for scalar, V for vector. Yes. All right. Outside temperature 15 degrees. Scalar. Truck traveling 60 kilometers per hour. Scalar. Water flowing due north at 5 kilometers per hour. Vector. Wind blowing south. Neither. Upward vertical force applied to a rock. Vector. Rock having a mass. Scalar. Car speeding eastward. Neither. Bulldozer moves a rock eastward 15 meters. Vector. Stone dropped into a pond is sinking at a rate of 30 centimeters per second. Vector. Oh, you have a couple more? There we go. Here, I bet you they're on my next page here of that one. No, I don't have them on there. We have these ones. Which one was the last one that we did? That's a vector. Wind blowing from the south, K, that would be a vector. This is a vector. This is a vector. So the way we draw a vector is with a straight line and an arrowhead. And we have some options with the arrowhead. Sometimes in textbooks they put the arrowhead in the middle of the line. I find that lots of people like to put the arrowhead on the end of the line. Either is fine. You're just sort of used to putting it on the end. Now, back when vectors were part of the IB curriculum, you had to write a vector as a bold letter. How do you draw in bold is a little bit difficult. So you'll see that when many people are writing, they write it as a little arrow over the letter because it's easier then. And I actually I often just put one arrowhead over so I didn't have to lift my pen. with the little, just a single arrowhead. I think that's just for laziness sake. It's just easy to do it. Okay.
Or they show two arrowheads, but it's always an arrow.
Yeah. So I like that one for a vector. The bold was just ridiculous, and then the other ridiculous notation I thought was when you couldn't bold it, they underlined it, which I also thought, why not just put the arrow over top? Draw in italics. So now the connection between vectors and matrices is that, I'm just going to go like this. You can write a vector as a column vector, which sort of looks like a column matrix. In Oh. I do that because I like how it flips when I'm not having it in a binder, because I kind of make the notes so you don't have to have a binder.
Yeah, why not only do you make them so you don't have to, they do it so you can't even have a binder.
Okay, fair enough. So here we have a vector. You take a point, 6, 3. We call that vector OA, and we can write it as a column vector. The top number is your x value. The bottom number is your y value. Yeah, and we're going to instead write all our vectors with a little arrow over top. Is it a game? Good luck, good luck. So when we draw a vector, the length of the vector is the magnitude of the vector. So if you had OA, which was at 6, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, the length of that can be easily calculated by just doing a squared plus b squared equals c squared. You know this length is 6, this length is 3. So we would say that the length of OA is equal to 6 squared plus 3 squared, and then square rooting that, 18 plus 9, 36 plus 9, square root of 45. And you could reduce that if you wanted, or you can leave it like that. Okay. Now, just like we use sort of absolute value bars to find the length of something. If you think about, I'm not sure if you were ever taught, like absolute value of -3 is 3. Absolute value of 5 is 5. You probably got to a point with absolute values that you just sort of said to yourself, it just makes something negative positive and keeps everything else the same. Now, technically, the definition of an absolute value is a distance from 0. How far away is 5 from 0? 5. How far away is -3 from 0? 3. So that's why it makes everything positive. And so here, when we want to find the length, we use those same symbols, the absolute value bars, because you're finding the distance it is from the origin, and it has that same idea. Properties of vectors. If two vectors have the same length and the same direction, they are considered equal. They don't need to start in the same place and end in the same place. So all of those vectors, all in different places, would be all considered equal. because they're going in the same direction and have the same length. If you take a vector and multiply it by a number, so there's the vector v. If I multiply it by 2, it gets twice as long. If I multiply it by -3, it gets 3 times as long and goes in the opposite direction. They'll always be parallel. Then we call a unit vector a vector of length 1. Okay? We have standard unit vectors. If you go 1 to the right, we call that the vector I. If you want, you can add the little half arrows over these. If you go 1 up, we call that the vector j. They both have length 1, and these are called the unit vectors. So you can write a vector as a column vector, or you can write a vector in terms of its unit vectors. 6 in the x direction, we would write as 6i, add the little arrow over it, plus 3j. So you know how you had to remember to write plus c in integration? You have to remember your little arrowhead symbol for integration. I mean, for all your vector stuff. You can do that? Sometimes with the i's and the j's it gets... Okay. Yes. They go into bad places. This is a great example of how Microsoft Word does not communicate well with printers, or they match up on my computer screen, and when I try to print them on your diagrams, they're a little bit off. Okay. Oh my goodness. And there went all the ink. So can you see that starting here, you would go 3 to the right and 2 up. You would write this as 3i plus 2j. For matrix C, you are going 2 to the right and 4 down. So it'd be 2i minus 4j. Matrix B, 1 to the left and 3 up. And D, 3 to the left and 2, 4, 5 down. This would be writing them in terms of unit vectors. If you wanted to write these as column vectors, this one would be 3, 2. This one would be 2, negative 4, negative 1, 3, and negative 3, negative 5. One thing I find that's interesting with the column vectors is that it's really related to its slope. Can you see that the slope of this line is 2/3, but the column vector is written 3/2. And we do the same thing in 3 dimensions. And this is actually going to be one of the things that we find really nice about vectors, is we can do math in 3 dimensions, which is how most of our life is lived, right? Most of high school math is done on a piece of paper, so we stick to 2 dimensions because that's sort of the plane of the paper that you're working on. Yeah, I would draw on really thick paper. I would love if a new smartboard would come and be 3-dimensional, that I could actually like pick points and then draw things in. That'd be super cool. It's I don't know, you could throw you information this way and come back.
The interesting thing is vectors are not
Mm-hmm.
we were still expected to know I, J, and K on our exam. There was questions in 3 dimensions with a 3D vector.
Interesting.
They gave us a column vector with 3 dimensions on it. And then they gave us 3D coordinates as well.
Interesting. I'll have to look at that. I've only looked at your part 1. I haven't looked at.
I don't know if we needed I, J, and K specifically, but we did need to know 3-dimensional calculations.
Can we do 4D vectors?
We could. Okay. I, J, and K. So now we have our x-axis, y-axis, and z-axis. Basically, the way that you draw things in 3 dimensions is you imagine your x and y-axis to start with on a piece of paper, lay it flat. So this is still 90 degrees here. Can you imagine that laying flat on a table? And then you add a z-axis that goes up and down. So this is still a 90 degree here, and this is still a 90 degree there. Should be like this. There we go. Can you see all the different planes? Okay. So if you were drawing the vector -9, 3, 4, you would go -9 in the x direction, 3 in the y direction, and 4 up. Does the rectangular prism there make sense on where this would end? So if I do the x and y first, this point would be -9, 3. And then whatever distance going 4 up is, I have to take that distance and go 4 up from that point to find the end point of that vector. Now, the interesting thing for finding the magnitude of a 3-dimensional vector is that it is just the square root of a squared plus b squared plus c squared. I don't know if that would be the right letterings to use, but whatever your coordinates are. And you could prove this because if you wanted to, can you see that you could do a squared plus b squared equals c squared and first find this length? And once you have that length, you could do a squared plus b squared equals c squared to find your new length. Now, would you agree that the blue line that I wrote there is the square root of a squared plus b squared? Okay? Or in this case, v1 squared plus v2 squared. And then if I want to find the whole length, I would now add the yellow part and square it, plus the blue part and square it, and square root it. So I would take this part and square it, plus the yellow part, which was v3 squared, and have to square root all of that. And when you do that, you get all 3 added together and all 3 squared, which is really nice because it's a really simple formula and a nice extension of what you already knew from a squared plus b squared. And then we could go to the next dimension. Notation-wise, magnitude of v equals the square root of -9 squared plus 3 squared plus 4 squared, 81 plus 9 plus 16, 106. What's that? So this one, the length of u (3 squared plus 4 squared), which is just 5. The length of v, 1 squared is 1, 5 squared is 25, 7 squared is 49. And the length of a, 6 squared is 36, plus 9, plus 4. Oh my goodness. It works out nicely to a perfect number. Seven. Works out to a nice natural number. No. It, there are perfect numbers, perfect squares, but isn't, oh, isn't, am I getting my definitions wrong? But isn't 6 the first perfect number? Perfect number is the number whose factors, except for itself, add up to itself. Is that the word for it? I think that's called a perfect number. So for example, 1 plus 2 plus 3, those are the only factors of 6, add up to 6.
But when you root 6, it doesn't equal 6, therefore it's not a perfect number.
It's not a perfect square.
No, it's not a perfect number. Yeah. A perfect number, I think, would be rooted and equal itself. And
There is, I think, only 4, I think there's only 4 perfect numbers under 10,000, which is crazy. Anyways. So v is equal to 3a negative 7. And the length of v is 10. Find the value of a. So 10 would equal the square root of 9 plus a squared plus 49. Square both sides. A unit vector. So u with a hat is a vector of length 1 in the same direction as u. So here's a vector, u. We could write it as a column vector. 6, negative 3, and 2. Its current length, we already figured out in a previous question. The length of u was 7. I thought it was this one. 6, 3, negative. Yeah, different letter. Yeah. No, not copying. So we had already done a squared plus b squared and c squared of those numbers and got 7. So if this vector has a length of 7, can you tell me possibly what vector has a length of 1 in that same direction? A 7th. of everything that you had. Can you see that this would be one way that you could write your answer? And vectors act like matrices. If you were multiplying by a scalar, another way that you could write this would look like that. Or if you wanted to use, how many times do we have to write this? 3 times? You could write it with the I, the J, and the K. So here's 2 for you to try. Can you write unit vectors for both of those? Yes? You like that square root of 29? $61? Is that right? 9 plus 36 plus 16? Very nice. So if you can find a unit vector, so let's call vector u 5, -3, 2. Does it make sense then that our unit vector, in this case, if we add these up, 25 plus 9 is 34 plus 4 is 38. This would be our unit vector of that vector. So now we can make a vector of any length in that direction once you know a unit vector, right? It's sort of like you're going grocery shopping and you're kind of curious how much things are going to cost, and they say, well, I sell a dozen apples for, I was going to say $5, but current inflation is probably like $12. Well, $12 would work out nice, right? Because then you would know that one apple costs $1. And then if you wanted to buy 7 apples, you would just have to multiply by 7.
Provided that they don't do like a discount if you buy 12 at a time.
That's right. Which was very interesting for me. When I lived in South America, there was, in Bolivia, at least the stores that I went to, they did not have the North American idea that if you buy more, we'll reduce the price, right? Yeah, and even taxes. But they would have on their prices, if you would like to buy 1 can of Coke, it's $1. Then they would put, if you'd like to buy 2, it's $2. 3 of them, and they would list multiple prices that were multiples of the amount that you could buy with no added incentive to buy one over the other. It was...
But it is an incentive, because if you want to buy 5 of 1 can of Coke, then you have to do math in your head instead of just doing the math that they've already done.
They've already done the math.
5 cans of Coke.
And it might be that for the person selling it, then they also didn't have to do the math.
A price list like that, except it was every price was like a different ratio.
So in other words, if we wanted it to be a magnitude of root 7, we just take the unit vector and multiply it by root 7. We get a very not nice scalar in front of this vector. But that is the right answer. For not putting negatives. Yes. Vectors have direction as one of their key things, and the negative is part of that direction. Adding and subtracting vectors. So if these were places, town A, town B, and town C, if you wanted to get from town A to town C, according to these road maps, you could either go there directly, A directly to C, or if you wanted to visit grandma who lived in town B first, you could first go to town B and then go to town C. In vectors, we're really only concerned about where we started and where we ended. So AB plus BC would be considered the same as AC. Definition-wise, we call AC the resultant of vectors AB and BC. And we'll do questions with force. If you hook up a rope to this desk and one person pulls in this direction and another person pulls in this direction, these are physics questions. Adding those two vectors will result in that desk moving forward in a different direction.
So you're telling me I get to do physics without being given all of the formulas.
That's right.
This is integration all over again.
Integration all over again. Disintegration of physics.
That's just derivatives.
If we have a vector AB and we have the vector, if we call it U, then the vector B to A is just U in the opposite direction. So we can write that as negative U. So A is 2I minus j, and B is negative I plus 3j. So I'm going to write A here. I'm going to draw A in blue. There's vector A and vector B. In green. So if I wanted to do A plus B, that means you start with matrix A, or not matrix, vector A somewhere. It would start there, go there, and where you ended, you would add matrix B to that. And this is your resultant. So having drawn it out, my new answer is 1 to the right and 2 up. Now if I show the math with the column vectors before this, matrix A is 2, negative 1, and we're adding matrix B, which is negative 1, comma 3. We just need to invent some sort of mathematics, probably fairly complicated, I don't know yet, that makes that work. But let's do a couple more to see what we can do. Okay, so next one is B. You start with B, so I start with B in direction. And then it says minus A. So minus A would be the same as A, but in the opposite direction. So that's that purple one. I put that here. And this would be the resultant for the second one. If I look at my resultant, I'm going 3 to the left and 4 up. The second one's answer would be negative 3, 4. Again, matrix B, which is the green one, it's negative 1, 3, and we want to subtract matrix A, which is the blue one, to negative 1. And eventually we're going to try to figure out some sort of brilliant idea mathematically that we could see this without having to draw them out. And finally, the last one, you would have to take 2 of B, 1, 2 of them, and then add 2 of A. Oh, do I have enough in for 1? Yeah, it'll work. 2 of them. And this would be your resultant right here, which looks like we're going 2 to the right and 4 up. And here we would have 2 of B plus 2 of A and get our answer. So do you think we need to draw them every time?
Yes.
Good. Excellent. There's no other way other than some newfangled, more complicated method than even matrix multiplication. Or you can just imagine vectors like matrices, and it works out. So you can just multiply corresponding items, add them together, and you get your resultant. Nice. It's always nice when the math becomes straightforward and easy. It is nice. Wait, you don't want to keep going? To 3 dimensions? Oh, yes. So the idea is you can just add the components. So if you wanted to do P plus Q, here you have 3, negative 1, 4, plus negative 2, 0, 3. And you get 1, negative 1, 7. Second one, if you had 3, negative 1, 4, and you subtracted half of negative 2, 0, 3, you would get 3 plus 1, 4, negative 1 plus 0, 0, and 4 minus 1.5, 2.5. Yeah, that's a mistake.
What's that supposed to mean?
That's a negative 1. Isn't that, I thought that was pretty impressive. I'll make it more clear. There we go. Which is, if you think about having to draw this out, you have one vector in 3 dimensions, another vector in 3 dimensions, and then trying to calculate the third vector, what all its components are in 3 dimensions, that would be awkward, time-consuming, and not necessarily pleasant just adding the corresponding components makes it super easy. So you know A to B is that vector. You know B to C is that vector. How can you go from A directly to C? Mm-hmm. Here is another beautiful connection to matrices. Adding vectors, notice that the middle letters have to be the same. They don't have to be, but if you were trying to put this equation together, that only makes sense if the middle letters are the same. So AB happens to be 4, 7, negative 3. BC, negative 1, 2, negative 5. AC then will be 3, 9, negative 8. What would you do in this situation? You know AB, negative 3, 2, negative 6. You don't know BC, but it's going to equal AC. And you notice there's a 0 in there? So either at this point, I heard one of you say you could just subtract. You're right. We could subtract this one and get the answer. 4, negative 2, 11. Probably some of you could have seen the answer just in the first part when we wrote it that way as well.